Nuclear gets a pretty bad rep, and, well, there are some pretty good reasons for that.
In the towering mushroom, Japan could read its doom.
It was the first step in a nuclear nightmare.
The Soviet Union has suffered one of the worst disasters in the history of nuclear power.
A disaster of unknown proportions.
But what if we could have nuclear power without the problems? No meltdowns. No weapons. Oh, and a lot less waste. Well, there is a nuclear superfuel that's supposed to do all that.
Let me tell you kids about thorium.
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 We've known about it for decades.
Molten salt breeder reactors operating on a thorium cycle.
More than half a century ago, we built a reactor that was supposed to unlock thorium's potential. We desperately need clean energy, so why don't we have thorium power everywhere today? Did we stuff up on nuclear energy? In the summer of 1965, scientists at the Oak Ridge National Laboratory in the US state of Tennessee wrote nuclear history. They powered up a groundbreaking new reactor.
Molten salt reactor experiment went critical on June 1st, 1965.
It was fundamentally different from most other reactor designs, even up until today. That's because its nuclear fuel didn't come in solid form. It was mixed into the coolant, molten salt, that circulated through the system.
I would call the molten salt reactor experiment a stunning success. It did things in the 1960s that we still can't do in reactors today.
This is Kirk Sorensen, a self-proclaimed thorium evangelist. His company Flibe Energy is working on a modern version of the Oak Ridge reactor.
Come up with things that are going to make it easier and better and safer and faster. But at the heart of it really is the technology that was originally put forward by Alvin Weinberg at Oak Ridge National Lab in the 1960s and 70s.
The vision now is the same as back then, to generate energy from a neglected nuclear fuel, thorium. It's a weakly radioactive chemical element that's 3 to 4 times more abundant in the Earth's crust than uranium, which is what we mainly use to power reactors today. But thorium itself can't power a reactor, and we need to get a bit nerdy to understand why. Nuclear fuels we use today, like uranium-235, are fissile. This means when their atoms are hit by a neutron, they likely split, and release more neutrons that split more atoms, and so on. This nuclear chain reaction produces heat, which can power a reactor. But you can't split thorium-232, it's not fissile but fertile. When a neutron hits its atoms, it usually just absorbs it and turns into thorium-233, no chain reaction yet. Because after about 20 minutes or so, it decays into protactinium-233, which after about a month decays into uranium-233, and that does split.
So these systems do tend to need a startup, if you like, a bit of a startup boost or amount of fuel to get the ball rolling, if you like.
Paul Norman is a professor of nuclear physics and energy at the University of Birmingham.
And once that is happening, we can start to grow in from the thorium, this variant of uranium that keeps the system working.
Now, you could theoretically use thorium in a whole bunch of reactor designs, but liquid molten salt reactors are arguably the most interesting, as they, by design, promise unique advantages.
But it tries to kind of rewrite some of the initial rules.
For a start, they'd be pretty safe. They couldn't melt down, since the nuclear fuel is already molten. And even if it did become too hot, most designs would have what's called a freeze plug. This would melt at a certain temperature, and the nuclear fuel would just drain into cooling tanks.
And the beautiful thing about it is it's physical. It's baked into the laws of chemistry and physics themselves. It's not something we have to go and append on or try to engineer later. It just is that way.
Molten salt also has a fairly high boiling point, so you could run the reactors at comparatively high temperatures and low pressures. This would make them efficient and potentially cheaper to build. Molten salt reactors would also burn up a lot of their fuel. There'd be less radioactive waste coming out than in conventional reactors, and much of it would be mostly gone after hundreds instead of thousands of years. And in thorium molten salt reactors, you'd get virtually no plutonium, which can be used to make weapons. Though, strictly speaking, that would also be possible with uranium-233. Still, all this really seems like molten salt reactors and thorium are a match made in heaven. Which does make you wonder, If the people at Oak Ridge were already onto this way back, why aren't molten salt reactors, like, everywhere? The molten salt reactor experiment ran at full power for more than 13,000 hours and became the world's first reactor to run on uranium-233 produced from thorium. The people there even started calling it the mighty smooth running experiment, but then government officials pulled the plug. What happened? Well, for one, the experiment didn't always run so mighty smooth.
The experience with the molten salt reactor experiment in Oak Ridge was pretty bleak.
This is M.V. Ramana, a physicist who researches nuclear policy.
The reactor had trouble even reaching its design power level. It then did not run smoothly. It was shut down a lot. And in the 4 years that it operated for only about 40% of the time.
There were also questions about the materials in touch with the liquid fuel. The alloy, specifically designed to withstand extreme heat, corrosive salts, and radioactivity, showed cracking. It also didn't cope well with higher doses of neutrons. And there were concerns that a radioactive gas byproduct could leak into the environment. Tritium is so volatile that it could escape through parts of the reactor.
When you build something for the first time, you don't get everything right. You do find issues. That's why we build experiments.
All technical issues aside, though, the real reason why the program was ended was a different one. The Oak Ridge director Alvin Weinberg wrote, "Our problem is not that our idea is a poor one, rather it is different from the main line." And the main line was another type of reactor, the sodium-cooled fast breeder reactor. It was eventually favored over the molten salt reactor.
There were a lot of good reasons for that. That was a much better tested design at this point. There had been problems there too, but those were not as apparent as the problems with the molten salt reactor.
You might come across other explanations as to why the experiment was stopped. It was the time of the Cold War, after all, and thorium molten salt reactors wouldn't have given you easy access to plutonium. Also, the nuclear industry was making a pretty good buck on conventional reactors. Why would it have wanted a more efficient design that breeds its own fuel? It's hard to say how much or how little truth, if any, there is to these. All the same, the molten salt reactor experiment ended in 1973.
We would have had a very, very different world had we proceeded with this. But, you know, like they say, the best time to plant a tree is 20 years ago. The next best time to plant a tree is today.
And today, there's a whole bunch of companies working on different molten salt reactor designs with different features. There are, for example, concepts to fuel a molten salt reactor with radioactive waste from conventional reactors. Kirk Sorensen's company, Flibe Energy, is planning to build a small test reactor before the end of the decade.
We've gone through a number of generations of nuclear reactors and other technologies. You know, molten salt's been through one initial generation, and it's time to continue on and understand these advantages that can be infused into the design.
China is planning to start up a small molten salt test reactor on the edge of the Gobi Desert. And India, home to the world's largest thorium reserves, is also working on reactors to utilize them as part of its long-term nuclear strategy. So, is it second time lucky for molten salt reactors and thorium?
You know, there's one level of it which is sort of talking and saying you're going to do things. Well, the much more important aspect is to actually be doing it.
And, well, this might prove a lot harder than flashy 3D animations suggest. Yes, molten salt reactors are meltdown safe, but that's not the only thing that can cause a nuclear accident.
Any good regulator will be asking a lot of questions to a designer. How will this reactor behave if there's a fire? What if there's an earthquake? What if your operator presses this button instead of that button? Those are not easy questions to answer.
Regulators might require changes to reactor designs, which could make them more expensive to build, which would kinda take away one of molten salt's biggest drawcards. And remember the cracked components at Oak Ridge? Well, problems like these need to be solved as well, not just on paper, but in a real radioactive environment.
Under those sorts of conditions, of course, it's harder for materials to bear up. So there are almost invariably things like that have to be further researched and developed, and really that sort of confidence made that they can work okay within the extreme environment of the reactor that the materials sit.
And then, of course, money. There needs to be, like, a lot of it. To to fund all the research for one, but also to build up an entire infrastructure and supply chain from scratch.
In the last couple of years, we've had more capital than we've ever had before, and we've proceeded much faster than we ever had before. But it's still a very, very small amount compared to where we need to be.
So let's be clear, there's a lot of catching up to do. Commercial thorium molten salt reactors are still years away, at least, if they ever happen at all. So we shouldn't let this dream distract us from climate solutions we have available now. Did we take a wrong turn in the 60s? Well, only the future can really answer that, by solving all the challenges the team of Oak Ridge invariably would have run into. What's your take on thorium and molten salt reactors? Are they the power couple that will help save the climate, or nothing but a pipe dream? Let us know in the comments, and don't forget to hit subscribe because we have a new video for you every Friday.